Yes.
Is this a 7, a 1, or a 2?
I don't know. What does it say online? It looks like a 2 to me.
A 2? Okay.
It looks like a 2, but go look online. All right. Here we go. I'm like running around crazy this morning. So the grades for the test were actually really good. Something happened that I don't see very often in my 20 plus years of teaching, and that is our standard deviation was 13, which is one of the lowest I've seen, like ever. And what that means is that the grades are clumped together. You can kind of see it in the chart right here. The orange grade is exam 2, or the orange numbers are the exam 2 grades, starting with the highest grade on this test down to the lowest. And then the blue is the exam 1. So you can kind of see for students whether or not they went up or down. So like student number 10, you know, they went up, right? They did 74.2 on the first test, they got an 84. So looking at it this way, all but 3 students went up, right? And we had the same number of A's on this exam that we did in exam 1. We had way more B's though. Look, we had 9 B's instead of 1 B, and we had less C's. And the D's and the F's kind of stayed. I think we had maybe more people take the first exam. I've had a few people drop. So anyways, the average was really good, almost a B average on the test. And like I said, the standard deviation means that you're all kind of in the same boat. We don't have huge disparities between the grades. So overall, I'm pleased with this. Yeah. Any questions? No? All right, so no test corrections on this one. The average is already a B, so the grade's the grade. Now, I encourage you to go back and take a look and see what you got wrong. If you have any questions about that, let me know. All right? We're good? Okay. All right, well, I have more stuff for you here. We are going to start a new topic. Well, new topic. We're going to continue with the idea of implicit differentiation, but we are going to get into word problems. And so I'm going to pass this out. Each person should take like 2 or 3 of these. Let me get this chair real quick. Okay, watch out, everyone. Okay. Take a couple of those. Here's more. Here's more. 2 or 3. Take 2 or 3 each. I think I printed 120 of these or something. Some extras. Oh, I never gave you.
Yeah.
Oh, okay. Well, here, have more and more. There you go. Here's some extras. I'm going to keep one for myself. Everybody have one? Are we good? Okay, so what you're looking at here is a worksheet that helps you work through these word problems. It gives you some sort of like template to use. Now, there's a little disclaimer, like not every single problem we do will be, well, this template won't be perfect for every problem we do, but at least to get us started, it's going to help us kind of get things in order, organize our thoughts, and run through a procedure. All right, so let me open up our notes now. We are on the section related rates. So really, all this is saying here is that we finally have reached a point where we can apply the idea of everything we've done to word problems, which is where it really makes, like, you know, it counts, right, in the real world. So I already know that this is one of the 2 top sections in this class that students struggle with, okay? It's going to be, probably when you look back on Cal 1, you'll say, oh, related rates, that sucked. Most students look at it that way. So I realize it's going to be challenging, I realize it's going to be intimidating, but I do promise you that the more you practice this, you'll start to get used to it, you'll start to get used to the idea, all right? There are some expectations here. I do expect that you do have some basic understanding of geometry, trigonometry, basic formulas for areas, volumes, etc. Now, your formula sheets do contain basic formulas on them. If you look at your formula sheets, the first page has like a picture of a circle, and then it has the area of a circle, and then it has the circumference of the circle, and then it has a picture of a sphere, and it says what the area of it is and what this volume, right? Those are all there for you. But there might be some other things that we need that I'll kind of point out as we get to them, like, hey, this is something you should know, all right? So always remember you can go to Google or something and look something up if you need to when you're at home, all right? All right, so we're going to start with very simple problems, and then we're going to get harder and harder, all right? That's naturally what we want to do. But here's the kind of the template, okay? This is the idea. And I don't like to give like a set of steps before we do a problem, but I'm going to do it anyway. We're going to talk about the steps, and then we're going to do an example, and you'll see how everything lines up, all right? So first thing we like to do when we're doing these related rate problems is draw a picture of what's happening. So what we have to imagine is that in all of these problems, we have something that's in motion, something that's moving. And what we want to know is at a certain instant in time, exactly how fast is something moving at that moment in time. So it's think about like a wheel that's spinning, right? And then at a specific moment, you want to know how fast a point on that wheel is turning or moving, right? So, or a person's running, right? And then at exact moment, you want to know what their speed is at an instant. So for all of these problems, we want to first draw a picture, okay? We're going to draw a picture of the exact moment in question, all right? So there will be some like moment in time where we're almost like taking a snapshot, and we want to draw a picture of that. That on your sheet here, it's the first box. That's where we would draw a little picture. And then it says we're going to draw a picture of the general scenario. So that's the second box here. And what that is a drawing where nothing is fixed. There's no snapshot. We have to imagine that everything is still in motion. So anything that's changing, we have to represent with a variable. You'll see, all right? We draw it, we let variables be variables, and we let constants be constants. The next thing we do is we assign variables, rates, and constants. We write down, what is given to us in the problem, and we write down what it is we want to find. And that's on the right-hand side. You see where it says what you are given, and then below it says what you want. That's where we're going to write down whatever's given to us in the word problem. We're going to write down that information, and we're going to also state what it is we're looking for. And then, this is the big critical step. Once you figure out what you're given and what you want, you must come up with an equation. Nobody's going to supply it to you, okay? You have to find an equation that somehow relates what you're given to what you want. You have to find some equation that comes from the real world that is going to relate the two things together. Once you find that equation, then we will use the implicit differentiation that we've been talking about the last few days before the test to take the derivative of that equation. And then once you take the derivative, then you have a formula now that you can find instantaneous rates of change, and you'll plug all this stuff in and you'll get an answer. That's the template. Let's just do an example. Yes? Let's do an example. All right, so first thing I want you to do is take a look at this question right here. Let's say we have a circle, okay? Let's get some things out of the way before we try and do a word problem. Let's get some things out of the way. If I tell you that the radius of a circle is 3 feet, then can you tell me the area? If I tell you that you have a circle, and I tell you that its radius is 3 feet, can you tell me what the area is? Yes? What is the formula for the area of a circle? Pi r squared, right? So the area of this circle, the area of a circle is pi r squared. But we know in this case that the area, the radius is 3, right? So this would just be 3 squared is 9. So your area would be 9 pi, right? That we can do. We should be able to do, right? There's nothing new there. There's no calculus involved, no derivatives involved. All right, what if I tell you, different problem, what if I tell you the diameter of a circle is 2.5? Can you find its area? How? Yeah, so the diameter is actually twice the radius, right? So what you would do here to find the area is first you would take this diameter, take half of it. So what's half of 2.5? 1 point. So this problem is saying the diameter, I'm going to put capital D is 2.5. But the radius then would be half of that, so 1.25 is the radius, right? Half of it. And now that you have the radius, you can find the area using pi r squared, right? So the area then would be pi times that radius, 1.25 squared, whatever that is, right? So these two, again, no calculus involved, right? These are just things we need to know how to do. What if I tell you the diameter of a circle is 1 foot? Can you give me the circumference? Not the area, the circumference. Yes, I'm seeing yes. How would you find for this one right here? What is the circumference of a circle? Is there a formula? 2 pi r. 2 pi r is the circumference of a circle. Okay? And we know the diameter, right? The diameter is 1. So if the diameter is 1, what's the radius? Half, right? Half of 1. So for this particular problem, I would replace the circumference would be 2 pi times the radius, which we would say is a half, right? Half of 2 is 1, so this is just pi. Y'all are looking at me strange. Is this all right or not? Yes? Okay. You sure? Okay. What if I tell you the circumference of a circle is 100 inches? Can you tell me the area? This is a little harder. Give myself some room. If the circumference of a circle is 100 inches, can you tell me the area? So if I tell you the circumference is 100, can you find the area? Well, what do you need for area? Pi r squared, so you need the radius, right? Well, if I have the circumference, that's not the radius, right? But can we get the radius from this? How? What is the definition of circumference? We just said it was what? 2 pi r. So this is saying 2 pi r is equal to 100, right? That's what this is saying? And can you solve this for r? Divide by 2 pi on both sides. So if I divide by 2 pi, divide by 2 pi, these go away, get r is, reduce that, 50 over pi. That's my radius, right? 50 over pi. Once I know my radius, I come over here and I can get the area now, right? So the area would be pi times the radius, which we just said is 50 over pi, but that's squared. Let's go ahead and square that. Pi times, when you square 50, you get what, 2,500? Yes? And when you square the bottom, you get pi squared. And then these you can reduce, like there's 2 of these, right? 2 factors, so it becomes a 1, sorry, and that pi goes away. So you just get 2,500 over pi. Y'all with me or not? Y'all seem like y'all are, but you seem like you're ready on spring break, yeah? So if somebody gives you the circumference of a circle, you should be able to find the area by using this formula to get radius and then take that radius and plug into the area. Again, there's no calculus here, right? Have we taken a derivative? No, nothing, right? Okay, what about this problem here? It's the opposite, right? I'm giving you the area. What if I tell you the area is 24 pi? Can you find the circumference? So if the area is 24 pi, can you find the circumference? Well, what do you need for circumference? You need the radius, right? 2 pi times the radius. Now, the radius I don't have directly, right? But I can get the radius from this because I know that this area is pi times the radius squared. That's the formula, right? and I can solve for r. So let's divide both sides by pi, and the pi goes away. And then what? Square root both sides. So r would be plus or minus the square root of 24. And really, we can throw away the negative because the radius of the circle can't be negative. So we only have one answer here, which is root 24. And then we take that and we plug that in right there, and that would be our circumference. Okay, so this is just us having some knowledge of some formulas and manipulating them to get one quantity if we're given some other quantity, right? I expect that you can do things like this in order for us to move forward. I assume that you're somewhat comfortable with this sort of idea. Questions? All right, so in all of the problems above, our circle is in what we call a static state. Right? When I tell you that the radius is this, our circle is fixed, right? If I tell you that the area is this, then the circle is fixed. If I tell you the circumference is just some number, everything is fixed. Everything is static, not moving, right? In this section, we will not be interested in the static state of something. We want things to be in motion. We want things to be moving. So instead, we'll be asking questions about what we call instantaneous rates of change. More specifically, the way that the rate of change in one variable affects the other. That's what we're talking about here. The static stuff we just did, and we kind of understand. We want everything to move now. So here's your first example, an expanding circle. Take a look at this illustration. Notice that the radius, when you look at this animation, I want you to notice that the radius of this circle is growing at a constant rate. So let me go ahead and press play here. I'm going to speed it up a little bit. Let me speed this up. Okay, so the radius is the distance from the center to a point out here, right? Somewhere? So just for ease of explaining this, I'm going to just take the distance from here along the x-axis. Look at that point moving to the right. Would you all agree that that point appears to be moving at a constant rate? Like it's not speeding up, it's not slowing down. Do you all agree? That point right here? So this distance, this radius, is growing at a constant rate. You all buy that? The question is the area growing at a constant rate? Let's take a different perspective. Look at this number for radius. Look at how it's changing. And I think I'm going to speed it up a little bit more so we can kind of count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? That radius is growing at a constant rate. How about the area? Is that area growing at a constant rate? 2, 3, 4, 5, 6. What does that look like it's doing to you? Is it constant? Look in the very beginning. Does it look constant to you or not? I'll slow it down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How does that look to you? Looks like it's speeding up? Yeah? Does that look like that's speeding up to you? It is. It's hard to see it, but think about it. If I stop this at some point in time, let me go back here. Let's say I stop it right here. That circle, right? Let me move it to 2. Let me do my radius 2 here. I'll try and get close to 2. I don't know if I'll be able to get to 2 exactly. Let's just get close. Okay, right there, right? This circle has a radius, has an area of 13. So when the radius is 2, the area is 13.4, roughly, right? Let me grow that radius by 1. So if I move my radius out to out to 3. Oh, pretty close. Okay, so when I let my radius be 3, now the area is 28, let's just say. So this grew by 1, right? And how much did this grow by, roughly? About 15-ish, right? About 15, that grew by about 15. If I let the radius grow again by 1, do you think it's going to jump up by 15 again? Let's see. I'm going to go to 4. Right there, close enough. When my radius is 4, my area is now 49, almost 50, right? Let's say 50. So how much did it grow by? 22-ish, right? Do you see that when we jump by 1 here, it only grew by 15. When we jump by 1 again, now it grew by 22. See, this rate of growth is not constant. The rate of growth of the radius, I'm letting it be constant. The rate of the growth of the area is not. You can also look at it a different way. Go back to this. This area right here, oops, sorry, let me. Okay, right there. So that area right there, okay, is set, right? If I grow this by a little bit, let's just nudge this out a little bit to here. This part right here is what I add, right? This is the area that I've added to it, like that. Right, that's how much I've added. If I nudge it again by the same amount, now I've added this much more, right? And do y'all see that this outer ring is more area than this inner ring, right? Because it's a larger ring. Are y'all following this? Okay, I think you are. We'll see. So, notice again, the radius increases at constant rate. That does not mean the area does. So here's the problem, all right? Here we go. This is your first related rate problem. That was just a visual to kind of help you understand what's going on. Take a moment to read it. All right, so in this problem, the radius is growing at a constant rate. Yes? Constant rate. And do you see that when we see the word rate here, rate of, they give us this right here, 0.5 feet per second. That right there is a speed, right? Think about when you drive down the road, right? 40 miles per hour. Miles per hour is distance over time, right? Distance over time. This is feet over seconds. That's a distance divided by time. So what they're giving you here is basically the speed of the radius, right? They're giving you the speed of a radius. And in calculus, how do we get the speed of something? Yes, but what is the whole thing of calculus has been to be able to find the derivative, right? The derivative is a speed, right? It's a slope of a tangent line, but if it's a position function, then it gives us the speed, right? So what you need to see here is that this right here, this information is actually the derivative of something. They're giving you the rate of change of something, right? The derivative of what, though? What is this representing the change in? What? 0.5 feet per second is how fast what's changing? The radius, right? So the radius is changing, right? This is changing. The speed of the radius is this, right? Now, what do they want to know? What are we asking for here? How fast, right? How fast, speed, right? The speed of what? The area, right? The speed of the area. We want to know how fast the area is changing. So the rate at which the area changes is the derivative of the area. We want to know how fast that's changing exactly when the radius is 4 feet. Okay, this is our first problem. So I'm just kind of circling things, highlighting things. Let me start with this right here, and I'm going to start drawing pictures, all right? So the first picture I'm going to draw is the one for the instant. The instant in time. Well, if I read this problem, I have a circle, right? And the moment that they're talking about is when. When what is fixed? The radius is what? 4 feet. So what's happening is the circle's growing, right? The circle's growing, growing, growing. And at exactly the moment that the radius is 4 feet, I want to know at that exact moment how fast the area is changing. I know how fast the radius is changing, but at that exact moment in time, I want to know how fast that area is increasing. What's the rate of change of the area? So that's my instant picture. Nothing is in motion right here. My next picture is the general picture. And in the general picture, my circle is growing, right? So I have r here, and I'm not going to put r equals 4. I'm just going to put r as r because the radius is changing, right? Y'all understand the difference between these pictures? In this one, the radius is fixed. In this one, the radius is r, and so that radius can be anything, right? Okay, that's the first two. Now, let's write down what we're given. And then we'll write down what we want. By the way, I should point out that when you do this thing here, when you're drawing your pictures and you're writing down what you're given and what you want, you do not have to go in any particular order, okay? You can put what you want first, you can put what you're given first, you can do your general picture, then what you want. It does not matter. Totally up to you, all right? All right, what I'm given in the problem, right? The only real numeric value I have here is this 0.5, right, feet per second. And that's the speed of the radius, right? The speed of the radius. And it is a distance over time, right? Distance over time. So here's the way I'm going to write this. I am given the speed of something, so it's the derivative, right? The derivative of the radius with respect to what? What do you think? What is the denominator of this ratio here? Seconds, so time. I'm going to say the change in radius, right? The instantaneous change in radius with respect to time is equal to 0.5 feet per second. Does that make sense to you? We're given a rate of change in the radius. A rate of change is a derivative. So we represent this 0.5 as the derivative of the radius with respect to time. Okay. What do we want? How fast is the area, right? So we want to know what the derivative of the area is, right? The speed of the area. So I'm going to write that this way. D capital A dt. That is what I want. I want to know how fast the area is changing, the instantaneous rate of change in area with respect to time. That's what I would like to find. And I want to find it when? At the moment, what? The radius is 4 feet. Let me recap. I have a circle that's growing, right? I know how fast the radius is growing with respect to time. I want to know how fast the area is growing with respect to time at the exact moment that the radius is 4 feet. And so at that exact instant, it's almost like I took a picture right there at that moment. How fast was that area increasing? Got it? Okay. Now the next thing on here, notice across the top it has these steps. We've done number 1, we've done number 2. We've assigned variables and constants. Number 4, find an equation that relates the thing that you want to the thing that you're given. So what I mean by that is this. I need to find an equation that somehow relates this r variable, the radius, to the a variable. Any equation I can think of that involves a circle that connects the area to the radius? And we know one, right? There's an obvious one. We just used it a moment ago, right? So the equation would be area is pi r squared, right? That's an equation that relates the radius and the area of a circle together. What you do not want to do right now, though, is plug in 4 for the radius. If you plug 4 in for the radius, then you have made this a static problem, haven't you? We want to act like everything's in motion. As soon as you plug 4 in, everything stops moving, and then that would be like me standing here asking you how fast I'm moving, and I'm not moving, right? We need to act like everything's in motion. So we're going to leave that r as a variable, and we move to the next step, which is step 5. And it says use implicit differentiation, right, on this equation. So I'm now going to take the derivative of this implicitly, and I'm going to ask you, what do you think I should differentiate with respect to? A, R, or T? T. Why? It's moving, yes, but like if I take, let me do it over here. If I took this equation, I could differentiate this. If I wanted to, I could take the derivative with respect to A if I wanted to on both sides, couldn't I? I could, right? But am I ever going to get something like this or something like this out of that if I don't differentiate with respect to t? No. So yes, I could do that, but it doesn't help me in this problem. I need to differentiate with respect to time because my information in the problem has to do with time. So I'm going to differentiate with respect to little t on both sides of the equation, right? So I don't want to do this. I'm going to take the derivative with respect to time of the left side, and then the derivative with respect to time of the right side. And let's see if we have an understanding of this differentiation. Oh, I forgot to mention, on your test, right, that you got back, I think, how many problems were there? 13. So I graded it off of a scale of each problem's worth 10 points, so there were 130 possible points. So if you missed 10, you get 120 divided by 130, that would be your grade. If you're trying to figure out how I got your grade, that's what I did. All right, what is the derivative of A with respect to t? Yes? Yes?
So would we ever have a problem that would, like, see how on a given interval or
Uh-huh.
given like pt?
Yes.
Would we ever have one that's, they're not the same, like if pt and then something?
You could have different ones, yes.
How would we figure, because like here it seems like that's how we figure it out. Like we're like, okay, both have this value. We solve
Yeah.
this. How would, I guess
I think we're just going to have to do one to see it, yeah. Well, you're asking, will we ever have a different variable down here on the bottom? In this class, no. Not that I can think of a problem. No, I don't believe we run into one where we differentiate with respect to something different for each one. It should be with respect to the same variable.